Hello. Here you see we were in the last class discussing about the Bode page plot. So the second type of example, in this case we will consider, say gs is equal to 10 into s plus 3 by s into s plus 2 into s square plus 2s plus 2. So what is the difference between the two types of transfer functions? Previously we have considered one transfer functions, and now we are considering another transfer functions. Here you see there is a pole at s is equal to 0. That means this is a type 1 system, right? And this is a second order factor. So if this type of transfer functions are given to you, how we have to calculate the phase corresponding to it. And once the phase is calculated, now you can know, you can be able to just draw the Bode plot in semilog graph paper. That procedure already you have developed. Now first stage, what you have to do, we have to just get the sinusoidal transfer functions by putting s is equal to j omega, as you know. So j omega equal to, this is j omega plus 3, you know, this is j omega plus 2, and j omega square plus 2 j omega plus 2, right? So during the getting the transfer functions, that is in sinusoidal transfer functions, to get the phase of any system, you may or may not use that, you know, that is your time constant form. In time constant form you may choose or you may not choose, but here without choosing the time constant form also you can get the phase. See, this is 10 j omega plus 3, right? And next, this is, I can write it like 0 plus j omega, because real plus imaginary, that complex part is need to be taken care of. And see, this is 2 plus j omega. I will write the real part first here, and here you see j omega square. So j square means minus of 1. So 1 j square means minus of 1. So this whole term becomes 2 minus omega square. Why 2 minus omega square? Because 2 is real, and from here we will get the real term minus omega square, because j square becomes minus 1 plus j of 2 omega, right? Now this is your real part and this is your imaginary part. So next step of it is to find out the phase of the numerator. Step by step I am doing, because once you understand all these things, then you can do it in a single step, right? So next step, that is phase of numerator. So numerator having two terms, 10 means 10 plus j0. So the term corresponding to, that is phase corresponding to, will be equal to 0 degree, and here real and imaginary, so tan inverse of imaginary by real, so tan inverse omega by 3. Next, phase of denominator. So what is the phase of the denominator? We'll get, this is 0 plus j0, sorry, j omega. That means what is the phase? Tan inverse omega by 0. So tan inverse infinity means 90 degree. That is a very good observations. In any system you find, if there is a pole at s is equal to 0, that means pole at s is equal to 0. If there is a pole at s is equal to 0, that means it is contributing an angle of 90 degree in the denominator. So if there are two poles, say s square is equal to 0, what does it mean? That means at s is equal to 0 and s is equal to 0, so there will be two poles. So for each of the pole you will be having contribution of an angle 90 degree. So total angle will be 180 degree, right? So angle of the denominator, you see here, this is 90 degree. So 90 degree plus of tan inverse imaginary by real. So this is tan inverse omega by 2 plus tan inverse imaginary by real. So that is tan inverse 2 omega, that is the imaginary part, divided by 2 minus omega square, right? So this is the phase of the numerator and phase of the denominator. So total phase of the system phi, that is equal to phase of numerator minus phase of denominator, right? So phase of the numerator minus phase of the denominator. So numerator is equal to, here we will write tan inverse omega by 3 minus 90 degree minus tan inverse omega by 2 minus tan inverse 2 omega by 2 minus omega square, right? So this is the overall phase of the system, and once you know the overall phase of the system, what is the next step? You have to find out the table. That means you have to make the table which will give you omega versus phi. That means for every value of omega you have to calculate the value of phi, and once this table is completed, now you can draw the actually Bode phase plot in the same plot, where in the upper side of the phase graph you have drawn the Bode magnitude plot, right? So this is the way, and you know the range of frequencies, how to choose the range of frequency. That means that will be your 0.01 initial frequency. Next you have to take the time constant for each of the term. For that term you will get corresponding corner frequencies, and you take all these corner frequencies, and in between there will be certain points to get the smoother graph. And next step, what you have to do, you have to just consider the last frequency, which is actually last frequency means the frequency which is actually normally taken, we are taking as the 50 times larger than that of the maximum corner frequency available. And this is all about the phase Bode phase plot. And the next class we will discuss about the stability of the system in frequency domain by using this Bode diagram analysis. And once you go for the next class, that means to get the stability of the system, you need to understand you need have a clear understanding of this Bode magnitude plot and phase plot, because in a single plot, single graph, if Bode magnitude and phase plots are given, then only you can get the stability of the system by using the Bode diagram. Thank you.